And welcome back. As we continue our cosmic journey, let's go ahead and wrap things up by talking about the future of large telescopes. So when we start looking at future telescopes, researchers are no different than any other field because we're always looking at different things. So astronomers and engineers are going to work together on different technologies that allow us to explore even more distant parts of the universe and to see them more clearly. Now, the premier space facility for the coming decade will be the James Webb Space Telescope. Of course, because it's recently launched, the work is just beginning, but its flawless deployment in the first half of 2022 has given astronomers a strong sense of optimism about its ability to probe the infrared universe. Now, the smaller Hubble Space Telescope is still functioning after more than 30 years in space. Now, NASA is also looking at launching the Nancy Grace Roman Space Telescope, which is another infrared instrument which will have a smaller mirror but a wider field of view than that of the Webb telescope. And what are some of the other plans that we might have besides just a couple of space telescopes? Well, on the ground, astronomers have actually started building the Vera Rubin Observatory 1, which has an 8.5 meter telescope with a significantly larger field of view than any existing telescope. It will rapidly scan the sky to find transients, phenomena that change quickly, such as exploding stars, chunks of rock, that are orbiting the Earth. Now, the International Gamma Ray Community is planning the Cherenkov Telescope Array, or CTA. This is 2 arrays of telescopes, 1 in each hemisphere, so we'd have a much larger array. Remember, the larger these arrays are, the more powerful they can be, which will indirectly measure gamma rays from the ground. Now, the CTA will measure gamma ray energies 1,000 times as great as the Fermi telescope currently can detect. And while we're talking about different wavelengths, let's talk about visible and infrared. Now, several groups of astronomers around the globe are interested in studying visible light and infrared light, and they're exploring the feasibility of building ground-based telescopes with mirrors larger than 30 meters across. It is technically impossible to build and transport a single astronomical mirror that's 30 meters or larger in diameter. Just think about that trying to go down your road. It's not going to happen. Now, the primary mirror of these giant telescopes will actually consist of smaller mirrors that are aligned so that they effectively act as one very large mirror in combination. Now, the most ambitious of these projects is the European Extremely Large Telescope, or ELT. The design of the European ELT calls for a 39.3 meter primary mirror, which will follow the Keck design, and what that means it will be made of 798 hexagonal mirrors. Each are only 1.4 meters in diameter, and they're all going to be held precisely in position so they form a continuous surface. And, of course, we can't have this discussion without talking about giant telescopes. International consortia with major contributions from U.S. astronomers have developed plans for the construction of 2 large new telescopes. One is a 30-meter telescope, or DMT, which will use 492 hexagonal elements. Now, each segment is 1.44 meters across corners. The segments are close spaced with gaps between the segments only 2.5 millimeters wide. We also have the Giant Magellan Telescope, or GMT. It's the second ELT project with a major participation, again, by U.S. astronomers. The GMT is a segmented mirror telescope that employs 7 stiff monolith 8.4 meter mirrors as segments. So you're starting to notice that with these technologies, we're getting into these segmented mirrors rather than relying on a single one. Now, these giant telescopes will combine light-gathering power with high-resolution imaging to enable astronomers to tackle many important astronomical problems as we continue to explore space.